What is up, fellows? Hello, class. I haven't written it down on my board yet, but today we're gonna be we're gonna be looking at how we can fundamentally change an integral involving bounds, involving x's and y's and stuff. I think we should just jump right in. Man, stuff in my face. Okay, we're gonna have a function. I'm gonna draw probably. Let's start with the kind of simple one, like y equals x squared. Now it's important that this is, I express that this is y equals x squared, right? This would be a kind of a rough graph of that, where this is the y-axis and this is the x-axis here. Let's scoot over, right? Okay, so if I wanted to integrate this function, say from 0 to 4, right? Well, traditionally, if you think of an integral, we're going to be adding up all these areas of like infinitely thin rectangles and slices, right? So we would commonly express this as the integral from 0 to 4 of like x squared dx, right? Here, let me make this clear. This is dx. Now, this is our integrand here. What we are actually integrating is the function y equals x squared, right? But what if I told you there's another way we could do this exact same integral, right? Let's go back to this original equation, y is equal to x squared. Well, if y is equal to x squared, then, fun fact, x is equal to the square root of y. Technically, it would be plus or minus the square root of y, because here, when we take the square root of both sides, what we are doing is we're taking the square root of x squared, and that's going to turn into, plus or minus x, right? Or absolute value of x. That's an important thing to know, I guess. Kind of a little bonus side content to this video, like x to the 2/2 power, which is equal to the square root of x squared, is in fact equal to the absolute value of x. That'll come in handy a lot when you take calculus 3. Right? Trust me on that one. So, if y is equal to x squared, then x is equal to square root of y, right? We're going to be worrying about the positive part of square root of y for the purpose of this video, but now ask yourself, what would the graph of square root of y be? X equals square root of y. Well, let me first redraw y equals x squared. It's the xy axis. Okay. Now, you may have guessed it, the graph of x equals, I guess, positive square root of y looks the exact same on the xy axis, right? These curves are the same thing. We've changed nothing except we've essentially just rearranged our variables in a way that we can do some nice things with integration. Now, going back to how we integrate functions, if at this y equals x squared function, we're going to be multiplying kind of the function value y at any point times the infinitesimal width dx, right? And what that's going to look like is we're going to have a bunch of slices like this, and they're going to be infinitely many, and we're going to add them up all the way until x equals 4 here on this axis. Now, we can think of integration in a separate way too, because all we're calculating is an area under a curve, right? So let's say we still want to integrate from x equals 0 to x equals 4, right? We're still going to worry about this line here. We still want to calculate the area under this curve. We can also take y slices. Hear me out. We can take horizontal slices of a function dy, right? Infinitesimal y lengths. And we can, with that, calculate an area of a function, but with respect to y, right? So here, for example, we could write this integral from 0 to 4 of x squared dx is going to be equal to the integral of, okay, we'll get back to the bounds on this later, but it's going to be square root of y dy, right? And now this index here, which is our infinitesimal, is going to correlate to the variable we are taking the integral with respect to. kind of like if you were to remember back to derivatives, how we have like dy dx, you're deriving, or you're differentiating y with respect to x, right? Here we're integrating y with respect to y, but this also gives us a hint at the orientation of our infinitesimal slices. If they are dy, then they're going to be parallel to the x-axis, right? They're going to be perpendicular to the y-axis because they're going this way, right? But they're going to represent a width that can be represented as a change in y, right? Like a change in y, but then here it's like a change in x, right? An infinitely small change in x, an infinitely small change in y. Okay, getting to the bounds on this now. Our bounds also have to be with respect to y. Now on this function, we were integrating x, like with respect to x, from x equals 0 to x equals 4. Now here, we're going to be integrating from y equals 0 stays the same, but we need to find an upper bound on this. And the upper bound is going to be a y bound, and it's going to be the y coordinate that corresponds to this x upper bound, right? So, okay, if x is equal to 4, then y must be equal to 16. And that follows with both of these equations. If I were to plug in x equals 4 here, I would get 16. And then same here, if x is equal to 16, or if x is equal to 4, then y must be equal to 16. So the upper bound on this is going to be 16, right? Now, well, there's one more thing I forgot. So that area would actually calculate this part here that I've just drawn in blue. Let me show you how to actually get the proper area there, because I realize now that I just kind of made a mistake, right? Okay. If you remember back a while ago when we talked about how you can break up integrals, like for example, I believe I used integral like x squared plus x dx. You can split that up into integral of x squared dx plus integral of x dx, right? Now we're going to be doing a similar thing here. Going back to that graph, this is going to be x equals square root of y. Right, now we want this area here. Now, if you were to rotate this, it looks a lot like kind of like what we would see on an like kind of an XY graph. It looks more normal, right? And we're getting an area. However, you see we're getting this area that's above the curve and not necessarily below the curve. So we can think about this as a difference of integrals, right? We can think of this as the integral of, okay, we know that this line here is x equals 4. So I claim that if we have 4 minus square root of y dy, that's going to get us this area. Now hear me out. That's because, and I didn't put bounds on this, this would be from 0 to 16. Proof, look back in the video, right? This is going to be equal to the integral from 0 to 16 of 4 dy minus the integral from 0 to 16 of square root of y dy. Now, I'm going to redraw this graph. The integral of 4 with respect to y, x equals 4 with respect to y, would give us this area here, right? But if we have that, that x equals square root of y function, now we're specifically confining us to this spot here. We're kind of bounding our area, right? So I realized I made a mistake a couple minutes ago in that video, but that method just described is how we would actually calculate that little area there, right? And so this is a clever trick, because sometimes it's a lot more useful and a lot easier to take an area with respect to a y coordinate instead of an x coordinate, right? Let me give you an example, and it's going to use the same kind of method that we just used. Let's have, how about just kind of, I'm going to draw like a piecewise function, right? It's going to look like this. Now this function, this is like a little like sharp corner here, a cusp. It's not going to be differentiable, but we don't care because we only care about integrability, right? And if a function is continuous, it's going to be integrable, right? We're going to be able to take the integral, right? So I want to find this area, right? Now we can find this area in two ways. We can look at a dx integral. However, because of the nature of this integral, this isn't one function. This is going to be some piecewise function, like f of x is equal to, this looks something like maybe x squared, and then this is probably going to be like negative x minus 4 squared, right? So we're going to have to do two integrals, actually. We're going to have to do an integral from 0 to, I don't know, some number b, wherever this like point is. We're not going to actually go through this calculation, so we don't need to worry about it too much, of x squared dx, and then plus the integral from, and then b to, okay, whatever upper bound is. Let's just say it's like 20, right? And then of negative x minus 4 squared dx, right? And so we could do this with respect to x, but it's going to take two integrals because we have two different of our upper bounding functions. We can't just lump this all into one integral because we'd have a conflicting integrand. We can't simply do that, right? You can combine the integrals with like the bounds and stuff, like remember like the kind of cross thing that we talked about a long time ago, but the integrands have to be the same, right? You have to be integrating the same thing. We can't do that here because they're separate. However, we can do a kind of a y integral, an integral with respect to y, if we recognize that that would be the integral from, 0 to, okay, wherever this cusp is. Let's just call that upper bound c. That's going to be a y equals c value. It's going to be here. Let's call this point b comma c for reference, right? Now we can recognize that this would be the upper bound of a y function. Remember, if we turn this around, this looks like an upper bound, this looks like a lower bound. So let's write in our integral. We can do negative x minus 4. Oh, I forgot. We have to actually change our function, right? So, kind of getting rid of the integral for a second. If y is equal to x squared, we know that x is equal to y, square root of y, right? And again, we're going to be worrying about the positive side about this. And if y is equal to negative, oh boy, x minus 4 squared, then, okay, square root of y is equal to negative x plus 4, right? X is going to be equal to, okay, here, I guess let's do this in multiple steps. Negative x is equal to square root of y minus 4. Sorry, we're doing a bunch of algebra here. And then finally, x is equal to 4 minus square root of y, right? Okay, 4 minus square root of y and square root of y. Let's remember those. I'll even rewrite them down. 4 minus square root of y and then square root of y. Okay, we can have an integral from 0 to that point c of, now our upper bound is going to be this 4 minus square root of y function, right? Because it's further to the right, it's further along the x-axis. 4 minus square root of y, and then our lower bound on this function is going to be minus and then square root of y. Cool. dy. And you could do a little bit of algebra to simplify this integrand if you would like to, or you could split this up into two integrals if you wanted to do two integrals. I mean, we did this in order to not do two integrals, so I personally wouldn't. Yeah, okay. Anyways, that is a way we can integrate a more complicated function that might not be differentiable, might be a piecewise function if you look at it with respect to x, in one integral with respect to y. Right. So, I hope you found this video helpful. Sorry for making that mistake kind of at the beginning, but it was a good learning moment. So, see you all later. Have a very nice day, class. Goodbye.